So this is going to be exercise 51 on page 21. This exercise is still about finding the equation of a polynomial, and in fact we are dealing with a fourth order polynomial. So what does this mean? Fourth order means, let's call our polynomial f, then the equation of our polynomial looks like this. So remember, fourth order means highest power of x appearing in the function equation is 4. So what is our problem? Well, our problem is the same as always. We need to find the values of a, b, c, d, and e. Okay, so let's start. What do we know about the polynomial? First of all, the polynomial is symmetrical with respect to y-axis. So what does this mean? Well, if a polynomial is symmetrical with respect to the y-axis, then the function equation only contains even powers of x. So this here is 0 and this here is 0 as well. Don't forget, here the constant standing alone is also counted as an even power of x, so this e here remains in the function equation. So instead of this function equation, we have the following function equation. Like this. So you see here why these symmetries are so important. If we consider this equation here, it seems to be the case that we need 5 equations to solve the exercise. In fact, however, we only need 3, right? Because we know, due to the symmetry, that b and d in the function equation are both 0. So we need 3 equations and not 5. So, because of the fact that the polynomial is symmetrical, we can reduce the number of equations we need from 5 to 3. Okay, so we need 3 equations. Let's see, what do we know about the polynomial? First thing we know is 0.14 is a point of inflection. Now the important thing here is that this single statement contains 2 equations and not only 1, because this statement means 2 things. First, it means that this point here lies on the graph. And since this point lies on the graph, well, we can plug the coordinates of that point into the function equation to generate a first equation. So let's plug the coordinates into the function equation, which leads to 4 equals 8 times 1 take to the power of 4, which is still 1. So can just ignore that, plus c times 1 to the power of 2, which is still 1, so no need to write that down like this. So this is already my first equation. Let's consider the second one. We know in addition that this point here is a point of inflection. So, well, what does this mean? According to the definition, the second derivative in a point of inflection is 0. So we know that f double prime of 1 equals 0. So this is just due to the fact that we have an point of inflection with x coordinate 1. So what do we need? Well, of course we need the derivatives, so let me just write them down. So this is my second derivative. Now I plug 1 into the second derivative and set the result equal to 0, which leads to 0 equals 12 times a plus 2 times c. and that's already my second equation. So I need just one single additional equation. So what else do we know? Let's continue with the exercise. Well, the tangent of inflection in P intersects the x-axis at x equals 2. So the tangent in P intersects x-axis at x equals 2. So this is the main problem with the whole exercise. What can we do with this? Well, the approach is the following one. If you consider this sentence here, well, what do we know? We know first that this point here lies on the tangent, and in addition we know that this point here, or to be more precise, that this point here lies on the tangent as well. So we know that point P and point Q lie on the tangent. So what can we do with that? Well, the idea should be clear. A tangent is a straight line. We know 2 points lying on that straight line, so we can find the function equation of that straight line. So the tangent is given by y equals m times x plus q. And well, now we can find m and q with the help of these 2 points. One approach is just to plug the coordinates of p into the function equation, leading to this, and the coordinates of q as well, leading to this. And so we get a system of linear equations with 2 equations and 2 unknowns, so we can solve that with the calculator, which leads to tangent equals y equals minus 4 times x plus 8. And now, well, maybe it's not completely obvious why this is a good idea. The answer is the following one. Consider this minus 4 in the tangent equation. This minus 4 is the slope of the tangent. That's the slope. And the slope is, well, and that's the core idea of differential calculus, the slope is the derivative. So we know that f prime of 1 equals minus 4, right? Because we have here the slope of the tangent, and this here is also the slope of the tangent, so these 2 things have to be the same. And now we are done, because this one here will lead to my third equation. I take this first derivative up here, plug 1 into the first derivative, and set the result equal to minus 4. So this leads to this. And this is my third equation. And with this, I'm done. I've got 1, 2, 3 equations. I've got 3 unknowns, so I can take my calculator and solve. And this leads to y equals 1 over 2 times x to the power of 4 minus 3 times x squared plus 13 over 2. And that's it. That's the whole exercise. Thanks for watching. I hope you liked my video. Bye.